Hello and welcome. In this video, we're going to discuss some of the data analysis steps for experiment 2, the enthalpies of sublimation of compounds. So let's begin by looking at a couple of the equations that are important here. So we discussed last time the beta equation, the escape parameter. If we're dealing with error analysis here, we have two terms, our L term and our D term, that contain errors. Our diameter, we're getting the error off the device that we're using to measure the diameters, and then the L term has an uncertainty that was provided by the manufacturer. And so we can look at this equation here. If we want to determine the uncertainty in beta, what we would do is take the partial derivative of the equation for beta with respect to, say, the thickness, square that term, multiply that by the error in the length, square that term, and then we're going to add the partial derivative of beta with respect to the diameter, square that term, multiply by the uncertainty in the diameter. So we're just using our ordinary differential error equation to give us the uncertainty in beta. Of course, this is going to be squares, and then at the end, we're going to take the square root of both sides. And so the important steps in doing an error analysis are looking at your equation, solving for the variable that you want the uncertainty in, and then looking at each of the variables and using their errors to propagate those into the value of interest. Another equation we discussed last time was the area, of course, pi r squared, and I mentioned that pi d over 2 squared might be slightly easier to use, and then you might even rearrange this to pi over 4 d squared. And then from here, you can then propagate the uncertainty of your diameter into the area. So what you're going to want to determine is the error, the delta A, the error in the area. And so then when we look at equation 13, our terms that contain error that we're going to propagate in are these 5 terms here. Okay, our molar mass, we're going to use enough digits so that it doesn't limit our results, and the same thing with the ideal gas constant. Look these up precisely so that they have as many digits as possible, 6 or 7 digits of significance are what we want to use. And of course, pi, we're not using 3.14. We're using, a much more precise value for pi. So that we're not using or introducing any sorts of errors into the equation that way either. And so we have our 5 variables. So we're taking the partial derivative of pressure with respect to mass, square that, times delta mass, square that, then add the partial derivative of pressure with respect to beta, square that, times delta beta squared, etc., until you go through all 5 of these variables. The time, there's a mentioning of the error of time later in the handout. You can look that up. I believe it's assumed to be about 20 seconds if you're doing the procedure in a efficient manner. The issue with time here, you may think, oh, how can you have an uncertainty with respect to time? Don't you keep it on the stopwatch? And the issue is really, at what time does the pressure begin to be low enough for the sample to actually sublime? So that's really where our uncertainty in time is that that we really are just kind of ballparking the pressure whenever it reaches a certain value and then starting the stopwatch at that moment. So there's a little bit of uncertainty when you may have started the stopwatch. That's truly where the uncertainty of time is really originating in this experiment. The temperature is a slightly tricky value to consider because the issue with temperature is really more the temperature bath's ability to keep a constant temperature. So this is really more of an illegitimate error than a random error. It's not like the temperature of the water bath is some real constant temperature and it's just our inability to measure it accurately or precisely that's really leading to the temperature spread. It's really more of a natural spread of the temperature created by the temperature bath itself. You can imagine the temperature bath is always going to be, warm, and it's going to cool down a little bit, then the heating element's going to kick back on. So the temperature is going to be fluctuating a fair bit, but hopefully we're keeping that fluctuation as minimal as possible through, setting the temperature in the display in a reasonable way. The best way is usually to keep the display temperature when you begin the experiment and set the temperature at that point, let it sit for a few minutes, and then carry out your experiment from there. But temperature, this could be a pretty big illegitimate error if you're not careful or if the water bath doesn't function particularly well in your experiment. So that's how you're going to deal with propagating those 5 errors into the vapor pressure value. And so then finally from there, you have equation 19. You may be plugging your values into equation 19. The key consideration here is that you're going to want to solve the equation for the variable of interest, the enthalpy of sublimation. And then you're actually only going to have two variables that contain error in this equation, just P1 and P2. Now you may think, okay, don't T1 and T2 have errors associated with them? And the issue is that, yes, there are uncertainties in T1 and T2, but they've already been propagated into P1 and P2. In fact, this is really what we mean when we think of like plots, is plotting um, the um, the dependent variable versus the independent variable. So when you think of the independent variable, that's like the T1 and the T2. It's independent of errors because we've already assumed them to be in the dependent variable P1 and P2. And so we're only really having these two errors here that we're propagating into our enthalpy of sublimation. Now, you might be a little bit confused once you solve equation 19 for the enthalpy of sublimation on how you're going to have two vapor pressures and do these derivatives, but it's really quite simple because what you want to do is take the partial derivative of the equation for delta H sub with respect to P2, where it's its own variable, and then square that and multiply that by the uncertainty in P2 squared, and then take the partial derivative of the equation for enthalpy of sublimation with respect to P1. That's a different variable from P2, so a completely different variable, so a different equation results, and then square that and then multiply that by the uncertainty in P1 squared. And so that's the general approach for the 2-point determination of our enthalpy of sublimation. And then later when you have, or at whatever point you have multiple data points and you're using equation 21, the key consideration here is going to be either doing that weighted linear regression and using a more sophisticated plotting technique and error technique to determine your slope and intercept. We can, again, talk about that approach in a different video. And an alternate approach would be just to use something like Linus. Use the Linus function in Excel. Again, there's other videos that have been made on the internet that are probably fine. I don't know if I need to make my own for that or not, but we can use Linus. You may have used this in the past to determine the your slope value and its uncertainty, so you can determine your enthalpy of sublimation with some uncertainty from the fit. So that's how we're going to handle errors into determining a vapor pressure with the uncertainty in the vapor pressure, and then using those vapor pressures to determine enthalpies of sublimation, propagating their uncertainties into the final results. All right, that's all for today, or for this video. Thank you.